Welcome to homework.
So once again, welcome to a new problem. This time, we still have a slit, and this is on diffraction and waves passing through slits. So the open slit itself, we're given the dimensions, and they happen to be 0.10 millimeters. Those are the dimensions of the slit. We can give it any value like that, but we'll see what happens. We can call that X, for example. We could call that X. And then there's light that's traveling to the other side. So, light is traveling at an angle, which is 30 degrees. So there are two parts to this. There's diffraction taking place. Remember, diffraction is when light splits, and so when light is passing through a small slit, it spreads out. So that's what we call diffraction. And on the opposite side, we do have a screen at point P that's able to accommodate the lights that are falling on the screen. And the waves themselves have a wavelength, and this wavelength is lambda equals to 589 nanometers. Okay, lambda is 589 nanometers, and this is P. It falls on P on the other side at an angle of 30 degrees. So our goal, that's the information that's given. So this is given. And then we want to find the phase difference. That's what we want to find. We want to find the phase difference between the Huygens wavelets. So I know you're thinking, what's this thing called wavelets? Right here, we have a wave coming in, and then when it splits into smaller waves, and those waves, we're calling them wavelengths. And so this is the phase difference we want to find out. It's kind of like a gap, so we want to find that out. And the phase difference is given by delta phi, and these are adjacent. So delta phi is equivalent to 2 pi over lambda, and then delta x sine of theta. So we're given theta as 30 degrees, and then we're also given delta x. Delta x is the general term for that's slit, but this slit delta x, we're gonna call it A. So this one we can call it A, and this is the central maxima right here. You could think of the central maxima running right there. And so our goal is to find the phase difference from the top, the phase difference from the top right here, from the top to the midpoint of the slit. So from the top to midpoint of slit. That means this whole formula, this is for the whole slit. So because we're going only up until the midpoint, we have to divide all of this by 2. And that changes the formula of the problem. So delta phi delta phi becomes equals to 2 pi over lambda times a sine of theta all over 2. So that's what we have right now. Remember, a is the same as the slit, the width of the slit. And so the next thing in the next page, we're going to do substitution. So we'll substitute the values that we do have. So delta phi becomes equivalent to 2 pi. Change the 589 wavelength into meters. So this is 1 meter over 10 to the 9 nanometers. That's on one side. And then A is the slit. It's in millimeters. So we have to change that to meters. 1 meter is 1,000 millimeters. So we change it like that. And then don't forget to multiply all that by sine theta. Obviously, we're thinking of our solution in terms of degrees, or our solution also could be in terms of radians. So that's the way we're seeing it. That's how we're thinking about it. And so if we go back, we see that this one has to be divided by 2. Why? Because it's half of it, half of the slit. It's half of the slit. So we have to divide everything by 2. If we don't, then we're not going to get the right answer. So the phase difference from the top to the midpoint. And then if we run those divisions, we end up having, our solution in radians. We could also change, we could change the radians to degrees, but then we end up having delta phi, when we solve for that, delta phi becomes equal to 160 degrees. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.